Good evening, I'm John Grant. I work in the Center for Earth and Planetary Studies here at the National Air and Space Museum, and I would like to welcome you all to the second in our Exploring Space lecture series this year. Programs like this are made possible by the generous support of our sponsors. I'd like to express my sincere thanks to Aerojet for sponsoring this program, and we're very grateful for the long-term support of NASA. I'd like you to join me in thanking them for their support. Well, we're very fortunate tonight to have with us Alfred McEwen, whom you've already heard a lot of answers to questions from. As I think you might know, Alfred is a professor for geology at the University of Arizona, and he is also the director of the Planetary Image Research Lab at U of A. As I think you heard during the Q&A session, he's been involved in a lot of planetary missions over the years. Past missions include Voyager, Galileo, Clementine, Mars Global Surveyor. Current missions include Cassini, Odyssey, LRO or Lunar Reconnaissance Orbiter, of course the HiRISE instrument on the Mars Reconnaissance Orbiter, and now he's the principal investigator for a camera that's being built for the Trace Gas Orbiter that'll be flown to Mars in 2016. Tonight he'll be telling us about the HiRISE camera and data from that instrument, and I'd like you to welcome Alfred as he tells us all about what's going on Mars.
Okay, everyone can hear me okay? I have too many slides here, so I'm going to go pretty fast to try to get done in 45 minutes. But the theme here is going to be that Mars is a dynamic world. Lots going on in the past and today as well. So Mars is a funny place because many landforms appear quite similar and comparable to landforms we have on Earth. It looks very, very familiar to us, but often seems better preserved because everything isn't eroded as much as on Earth with all this darn rainfall we have here. But Mars also has processes with no counterpart on Earth, particularly driven by the seasonal deposition and sublimation of dry ice, carbon dioxide. So I'm going to, in this presentation, introduce MRO and HiRISE and Mars and the Mars exploration program a little bit, show a few greatest hits, talk about ancient Mars, where we had quite a suite of Earth-like processes active, and then present-day Mars, which is still surprisingly active. So first, introduction to HiRISE. It's a big digital camera. Lower right there, right here, you can see that's the telescope part of the camera being installed on the MRO spacecraft. That's from Lockheed Martin Corporation in Littleton, Colorado. People for scale. Most planetary instruments aren't the size of people. The HiRISE camera itself was designed and built by Ball Aerospace in Boulder, Colorado. So what it consists of in the focal plane, besides the big telescope, is 14 CCDs, just like CCDs many people have in their digital cameras. 10 of them across the full field of view, and then an extra 4 that gives us color just in the center strip of the imaging. But this is different from our cameras, that this is pushbroom imaging. So the spacecraft orbital motion pushes the sensor projection across the ground and builds up the image as we go over the ground. And then so the line integration time, exposure time has to be matched to the speed. So we're going by very fast. It's like 19,000 miles per hour. And at one point, we did a little analogy. This would be like trying to image sands of grain on the highway while you're driving over it at like 60 miles an hour. That's the challenge. And so we have a very short integration time per line, but what we do that's unique then is we actually image that little patch of ground 128 times and add up the signal. And that means that everything has to be very precisely aligned. Some people didn't think this would work, but it's worked beautifully. So here's what the full HiRISE image looks like with a color strip in the middle. Now, many of the images I'm going to show you are just the color. I'll zoom in on just that color strip. Where are we in our exploration of Mars as of a couple days ago? We've acquired almost 19,000 images. A typical image is almost a gigapixel, so 15 terapixels of data. This is more data than all previous missions to planets combined. And yet, if this was all unique coverage, it would cover only a little more than 1% of the Martian surface. So there's a lot of surface area of Mars and takes a lot of data. Plus in color, it's only a fifth of that even. We've also acquired about 2,000 stereo pairs, but again, that's only 0.2% of Mars that's covered in that way. So this is an introduction, a chance to advertise my next camera, HiRISE, and this camera will be lower in resolution, but the whole thing is in color, and we get stereo with every image as well. So this is going to be a nice complement to HiRISE. So in HiRISE, we get stereo data. This is for 3D imaging of topography by pointing the whole spacecraft to the side and taking 2 images. But Mars changes, the illumination changes, so the images don't match perfectly. And then on HiRISE, we have a rotation mechanism. So while we're flying over Mars, we point forward, take an image, then rotate the thing around 180 degrees and re-image it all in an immediate pair of images. So we'll have color stereo images with every observation. With the stereo data, we can do fun things like make oblique views, as shown here, and work out the structural geology, for example, as a cross-section at the bottom there. And this is a little flyover movie from a stereo DTM. And it's really a black and white image that's given sort of a Mars-like color because, again, our color just covers this narrow strip. But this is no vertical exaggeration. That's what the terrain really looks like on Mars. We haven't landed ever in a place like this. We like to land in flat areas that are safe for landing. But much of Mars is actually very rugged and scenic, if we could get there on the ground. So I want to introduce Mars a little bit, just show you the major features, get you oriented to some degree. And so here's a couple of views. This is the altimetry data from Mars Global Surveyor. So red and white are high in elevation, blue is low in elevation. And we have the northern lowlands at a big low area. We have impact basins like Hellas and Isidis here. On the other side of the planet, we have this big high area called the Tharsis Bulge. And on top of it are these pimples. Well, those are volcanoes, and the biggest one, Olympus Mons, I think my cursor keeps vanishing when I do that. Biggest one, Olympus Mons, is about the size of New York and Pennsylvania put together, so it's not too small. And then we have Valles Marineris extending off from Olympus Mons. So down here is the same data, but now in a map projected view. And here are the landing sites. So first we landed Viking 1 here in Chrysi Planitia, Viking 2 here in Utopia Planitia in the northern lowlands. Then came Mars Pathfinder right next to Yogi Rock. Then came Spirit, then Opportunity, and then most recently the Phoenix lander here at high northern latitudes. So here, there's a lot of spacecraft that have been to Mars. Here are the ones that are active or recently active. Right now there's 3 orbiters. There's Mars Odyssey, MRO with HiRISE on it, and then ESA, European Space Agency, has a spacecraft called Mars Express. There's the Phoenix lander has completed its mission. There's the 2 MER rovers, Mars Exploration Rovers, Spirit and Opportunity on the surface. Coming up, launching this year in November, is the Mars Science Laboratory. This is a really big rover that's going to do marvelous things. In 2013, there's another orbiter that studies the upper atmosphere and climate change on Mars. 2016, is the trace gas orbiter with HiRISE on it, and there's also a lander demonstration this is from the European Space Agency again. And then beyond that, it's still being worked out what exactly is going to happen, but there's a strong desire to return samples, rocks from Mars. Okay, a few of the HiRISE greatest hits, the fresh impacts being among them, haha. But one of our first images when we were in the low orbit, just by coincidence, the Opportunity rover had just arrived at Victoria Crater when we got into our low mapping orbit. And one of our first images here was of the rover, and we were really pleased to see, we could even see the shadow of the PanCam mask, which doesn't show up very well here, does it? Color choice wasn't too good. But this is now our second most popular image, having been eclipsed by this one of the Phoenix lander descending onto Mars. And this is a little piece here blown up. That is the Phoenix lander on its parachute. It's about 10 kilometers above the surface, descending. It looks like it's descending into this big crater, but that's actually an illusion. It's well out in front of it. And furthermore, here it is in another blow up. It had released its heat shield just seconds before, and we actually captured that, the heat shield, in free fall. So this was a very fortuitous image. Now, the most popular image will be of the MSL lander dangling above the surface, so stay tuned for that. Mars has moons. We imaged Phobos here in enhanced color. Many of the color products I'll show you are enhanced because HiRISE has infrared color shifted to the infrared, and we like to enhance it to show you the subtle differences as well. And the other moon is Deimos. Two views of it. Okay, so now I'm going to talk some about ancient Mars. This is going back more than 3 billion years when Mars was more Earth-like and had a lot of activity. The background image here and the next image are from a region of Mars, Nili Fosse region, that is some of the best exposed areas of very ancient bedrock on Mars. And these ancient terrains are interesting because they contain much greater mineral diversity and color diversity than the younger rocks. And the reason for this is because water was more prevalent and altered the rocks into a greater variety of minerals. Now, with HiRISE, we just have 3 colors. We can't tell you what the minerals are, but by comparing it to spectrometer data, we have some idea. In general, the blue and greenish colors represent unaltered rocks like olivine and pyroxene rocks that make basaltic lava. And the light tones represent altered minerals of various sorts. You'll see these linear sharp ridge features in many images. Those are wind-blown sand dunes marching over the surface. We'll see those in almost every image. Here's a little flyover movie of the Nili Fosse region. This region is complicated. It's like the Earth, where the landscape has been shaped by a mix of impact cratering, volcanoes, floods and deposition from water, wind, and it's all jumbled together and hard to interpret. Another region where ancient rocks are really well exposed is around Marth Valleys, inside and outside the channel itself. And this region is rich in clay minerals, and clay minerals produce a variety of colors, much like the Painted Desert of Arizona, which is clay minerals with a variety of colors. This is one of the candidate landing sites from Mars Science Laboratory, and this is probably the best exposures of these ancient clay-rich rocks on Mars. This is a HiRISE color image, the long strip that's been cut up so it all fits nicely on one slide, in case you're wondering. So a very different type of deposit on Mars are these sulfate-rich sediments. So what is a sulfate? It contains sulfur. Basically, it's a salt of sulfuric acid-rich water. And gypsum is an example of a sulfate mineral if you've been to White Sands, New Mexico. But this produces some very distinctive morphologies. It's very easily eroded by the wind. This type of rock implies a very acidic water. It's water-rich environment, but very, very acidic. And the Opportunity rover landed on a terrain rich in sulfates, although it wasn't as well exposed as what you see here. I'm kind of moving from oldest to youngest, the progression here through. So slightly younger, but still very ancient, are these sedimentary rocks, which in some places have, well, really quasi-periodic layering. So we have sets of layers of very uniform thickness. And in this particular place, some places at least, there's two sort of chords to this where you have bundles and layers. So they're bundles of equal thickness, and each bundle has like 10 layers of equal thickness. And so this implies some sort of regular process that we think is periodic in time. And that could be the orbital variations of Mars, changes in its tilt of its axis and the eccentricity of its orbit around the sun and so forth over time, which somehow affects the sedimentation and induration of these layers. This is a pretty color image of Becquerel crater with some of these layers. So I wish this movie was in color, but here is a 3D view of this terrain. And this one, I'm trying to remember if this one has vertical exaggeration, and most of these do not. It shows you the true landscape. This one might be vertically exaggerated, but there you can see the stair-step pattern with two sort of step thicknesses. In one of the MSL landing sites, Gale Crater, there's a thick stack of these sort of quasi-periodic layers. If MSL lands there and it drives uphill far enough, we'll be able to investigate and hopefully better understand the origin of these. These are some more bedrock layers. I just threw this one in because I think it's beautiful as abstract art, cubism on Mars or something. Moving on to fluvial processes, we have giant channels on Mars that we've known about for some time. There are also depositional fans. John Grant here is a big fan of fans on Mars. Most of these fans occur at the edge of a basin, and they're either a alluvial fan that's maybe carried by water, but it's dry, or it could be a delta out into a body of water. This one here is unusual in that it forms in the middle of the basin. And it appears similar to submarine fans, for example, in the Gulf of Mexico. And an analog site for this is one such fan that's way out far into the Gulf of Mexico that Shell Oil has been studying as a potential petroleum trap. But because it's so far out, they gave it a nickname. They call it Mars. Okay, giant tree ferns, no, not really. These are mesas, plateaus that are elevated. But what we think happened is that these were river channels that got filled in with gravel or something that made it hard rock, resistant to erosion. Then billions of years of the wind blowing, stripping away softer stuff, left these behind high standing. Another one of the candidate MSL landing sites is in Holden Crater, and this is a little flyover movie here. This has some of the most regular and best examples of lake deposits. There are these layers that have the same elevation over a broad area in this crater. MSL wouldn't land right near one of these cliffs where it looks a little dangerous. It would instead land nearby and drive to these exposures. And they're may in fact have been 2 or more lakes in this region. Okay, moving on to even younger, maybe only 1 billion years or so ago, or even less than that, we have a lot of impact craters that are fairly fresh, relatively fresh and well preserved. And we see a number of interesting things with these impact craters, including this pitted, ponded material on the floor, which we think is related to the release of volatiles, such as water that's chunks of ice from the subsurface that either explosively or otherwise sublimate. And there's also fluvial features associated with these, or water-worn landscapes. Oops, let's see, went by a little too fast. So there's a color image of Mojave crater showing some of this fluvial erosion. This looks like the spitting image of the Mojave Desert, which is a very dry place, but they have thunderstorms. There's no vegetation, so the thunderstorms cause lots of erosion. And the name Mojave crater was suggested because of this analogy in this location. And here's a flyover movie of Mojave crater. This is without vertical exaggeration, very rugged terrain. You can see the smooth areas of this pitted and ponded material. And then there are these fans, alluvial fans and channels, both inside and outside the crater. We're now outside the crater looking at the slope away from the raised rim around the outside of the crater. And this is a surprisingly recent crater. Certainly probably something like 100 million years, which is young to a geologist, and yet it looks like it rained. So this is still a mystery to understand, how could it rain on Mars so recently, given what we think happened with the atmosphere over time. Volcanism. We have some very familiar looking features on Mars, including probable cinder cones. On the left is from Lassen National Park. And you typically get, over the vent, you get both a lava flow flowing out, and then you get places where the magma that's more charged with volatile, gets thrown out, and it freezes in the air and lands in cinders and makes a cone. So here on Mars, you see some features that look very similar to cinder cones, in this case, sitting on top of probable lava flow. This is a map. The dark area in here is all one lava flow from one event that erupted from up here, and there's some fissures. This is a flood lava. We have flood lavas on Earth, but they're not well preserved. This is remarkably well preserved so that we can really see its morphology. And this may be only a few million years old. So now we're getting almost present day. And some of the interesting features on top of this lava include these ring and cone structures. And these are somewhat like rootless cones or hornitos and so forth that form on lava flows when they flow over water-saturated ground, or in Iceland, they particularly like to form if there's a peat bog. These are a little different because from the structures here and the streamlining, it's clear that these formed as the lava was actually draining away. So there was a thick flow of lava that backed up, and then it drained away, flowing into lower areas. And as it drained away and removed the pressure on the base of this, that's when these features formed. Landsliding is another important process on Mars, continuing till today. This is a place in Valles Marineris, the giant canyon, where some of this layered sediments, like I showed you previously, landslided and made this deposit of jumbled blocks. And this is another one I like for Mars's art, Jackson Pollock on Mars, just random throwing rocks together. I think it looks nice. Mars has been affected by glacial flow of ice. And this is a nice example here of sort of a zooming in on one spot. So we start here with, there's another camera, an MRO called the context camera, that gives you a 30-kilometer wide field of view. So this is an ancient impact crater here. Here's the rim, there's the central uplift. And all along the slopes in this region, now we can zoom in on the reduced HiRISE image, we see these sort of flow-like tongues all through here. Zoom in on the HiRISE color here, and zoom in again here for the HiRISE to see the texture. So this looks very much like the lateral and terminal moraines of a glacier on Earth, where the lava flows downhill and pushes debris and deposits these ridges of debris out in front of it. And then the ice disappears, sublimates, probably on Mars. And what's interesting, we have stereo here. Right now, this toe of the flow is actually at a significantly higher elevation than this region here, where it appears to have originated. So that tells us that the ice was originally much thicker here. Continuing to the last thousands of years, we have periglacial processes. There's shallow ground ice. It expands and contracts with temperature, and this does interesting things like sorting boulders. So all these dark features here are boulders, some of which are kind of lined up and trying to make a pattern, and it almost looks like there's a message written here. It's probably my imagination, though. Okay, now present-day Mars. Mars is not a dead world. It's still active. So first we have the new impact events. We've been watching these happen. We've characterized more than 200 new impact events on Mars now. This tells us about the rate of bombardment. These are hitting Earth too, but they explode in the upper atmosphere, and we never know that they're happening here. How the patterns that these make, they break up in the atmosphere. That tells us about the properties of the bolides, whether it's a dense asteroid or maybe a very loose underdense cometary material. We see the different craters that form in different sorts of targets. We can watch how these patterns change over time. And we've seen some remarkably clean ice exposed, as I'll show you in a moment. Here's just an example of one of these events. That's a single crater, making a nice blast pattern from interacting. What happens is there's a shock wave in the atmosphere that disturbs the dust on the surface, and that makes a big marking that we can easily find. These are a couple of crater clusters. The one on the left here is interesting because it has this dark septa. We think that's from the interaction of two atmospheric blasts from the two largest craters that formed here from fragments. This one on the right, this is a different scale, but this is remarkable because there's thousands of craters that formed here. One bolide came in, probably cometary, and broke up, probably came in at a very shallow angle as well. That helps to spread them out. But broke up and made thousands of craters in one impact event. There's controversy over whether some of the great mammals from the last ice age, like the woolly mammoth and so forth, which became extinct suddenly, was it from a cometary impact, maybe like this, which didn't leave a crater behind? I won't say whether that theory is likely or not, but certainly this type of event does happen. So here's some of the fresh ice exposed by craters. And so for all of the craters that we found north of 43 north latitude, we've seen these bright white exposures. And from the spectrometer for the biggest examples here, we've confirmed that it is water ice. And we've watched these, once it's exposed, it's unstable, it sublimates. And we've watched how it darkens over time, and it's slow enough to tell us that this is remarkably clean ice. This was the surprise. We already had reason to believe that there was shallow ice, but it was thought to be probably dirty ice, where the atmospheric water vapor fills in the pore space between the particles. But instead, this is very clean ice, and so there's still interesting debates going on about how this formed. This ice is probably only something like thousands of years old, too. It's not an ancient deposit. So in any event, for future astronauts going to Mars that want drinking water, here is remarkably clean ice it's so shallow you could kick the ground with your boot and expose it. Also forming currently on Mars are these slope streaks. These form in dust-mantled slopes. And here's the top of the hill. This is a slope, and this is the bottom. And these are like snow avalanches where the dust gets unstable and avalanches down the hill and removes the brightest dust from the surface. And there's many of these that form every year. For the whole set seen here, this may be tens of years that it took for these to form. Here's one we found that was particularly interesting. We initially saw this from the context images, lower res. Here's the before and after image. And there's what looks like a slope streak, except it's very odd because it's got this stubby start to it instead of a very narrow start. It's very wide as well. So when we imaged with HiRISE, we saw a sharp, small impact crater, and we saw that the darkening pattern around here is similar to what we've seen around other new impact events. So we think this was one of these new impact events that destabilized the dust and made this big slope streak. Mars is windy, and sometimes we get lucky enough to actually image a dust devil that's active. This is not now something that happened years ago. It's happening as we took the picture. This is airborne dust being swirled around. It's moving from right to left, and it leaves a dark streak in its wake. There are many of these on Mars. The time of day of MRO is late afternoon, so we're usually past the peak of the activity. Blowing wind has shaped the Martian surface in many ways. This is, I just think, one of the most beautiful images because it shows this streaming sand coming off of these eroded mesas and making these linear dunes that then break apart into these Pac-Man-like features. These are called Barkan dunes, and the horns point downwind. So the wind is blowing from right to left. These, I'm certain these are active. They're still changing. We don't have before and after images to document it like I'll show you elsewhere, but I'm certain these are active. Here's a rare crater on the North Polar layer deposits, which is a young deposit and has very few craters. And it's being blown by the wind to make these interesting looking streaks here. So here's a few examples of time steps showing changes. This is the steep slope of a Barkan dune. These are the points of the dune. So wind is blowing from top to bottom, but 2 time steps. These are separated in time by 2 Mars years, which is, MRO has been active a little more than 2 Mars years. And it takes a while to see what's happening here, but you can see the features. Look at this feature there. It's migrating closer to the rim of the brink there. All of the ripple features and landforms here seem to be moving south. And in fact, if you look at, this is bedrock, that's stationary. If you look at the whole dune shape here, the whole thing is moving south relative to the bedrock. So we're seeing migrating dunes and even faster migrating bed forms on top of the dunes. And we've been discovering that sand is on the move over many places on Mars. This was unknown and debated for many years about whether these dunes were active or not. We have boulders rolling down slopes, and if you can see it here, there's a nice example right here, and you can see the trail. I don't know if you can see that, but there's a sort of skipping, bouncing trail there where it bounded down the slope. We see these on the moon as well. This is not unique to Mars. So here's something else that's happening as we took the image. This was quite a surprise when we first saw it. This is an avalanche. This is airborne dust that hasn't settled yet after material slid down this slope. And this is a very, very steep slope, about 60-degree slope that's on the edge of the North Polar layer deposits. And it's amazing that the slope can exist at this steepness, but what happens is it gets undermined at the base and keeps it steep. But we found this in 1 year and thought maybe we were just incredibly, enormously lucky to have caught this thing. So the next Mars year came around about 2 Earth years later, and we monitored these, and we saw a bunch of these around steep scarps, and they all occurred within a narrow time period. This L sub S divides the Mars year into 360 units, so a very short period of time. There's a polar avalanche season of a few weeks where these things are happening. It's when the sun in the springtime first hits these steep slopes, and we think it's CO2, ice and frost plus dust, and occasionally it drags some boulders of ice with it. Lots of activity in these North Polar Layer deposits. Here's an example where I'll show you again two time steps. And there's a couple things to look at. One is look at some of these boulders here that move and disappear. So they're moving down slope, but then they either move further down slope, or in some cases they appear to shrink. So this is probably ice that's exposed, and then it sublimates into the atmosphere. There's also, look at this piece right there. That just vanishes. So that whole chunk is downslope somewhere. And then if you look at these ripples closely, you can see that they're moving. Oops. That can be hard to see there. The viewing angle is slightly different from the two images, so the bedrock is moving as well. Here's another example, probably a better one, of ripple movement. So the sand is moving. The gullies are also active on Mars. These were caused a lot of interest when they were first discovered because they look like features formed by water on Earth, and they looked extremely recent. And they are extremely recent. They're happening today. We've seen these happen, and we've documented when they happen. And to our surprise, they are happening predominantly in the winter. They're happening the very coldest time of year when the ground is covered by this carbon dioxide frost. So liquid water is really not a viable hypothesis for these particular events. Instead, we think that the CO2 frost serves to reduce the friction between particles. It weighs down on the surface to some degree. We don't understand in detail, but that somehow is triggering these flows and making landforms that look very much like terrestrial landforms that form from water, but they don't seem to be forming from water, at least at the present time. Here's just a closer look at some boulders here. You can see boulders before here and there. And then later on, these boulders are gone, but there's new boulders here. Maybe those are the same boulders, or maybe these got buried and these are new ones, but clearly there was a change. So this activity is able to move, it's just boulders of up to 2 meters diameter, large rocks. Here's another site where the color data shows us really exactly what's been active. But zooming in on a piece here, we'll look in black and white at the changes. And what you should be seeing are a whole bunch of new lobes of material. Oops. And there's somewhere up here a boulder that, vanished, either buried or moved down slope. So these are debris flows that deposit material with a certain yield strength, so it makes a steep flow front when it's deposited. So here's a movie of another site. This is again in winter and spring, and it's a gully channel, and we see this dark material move down incrementally, and then suddenly the whole thing is covered by this dark flow. And again, this is happening with CO2 on the ground, so this is sand and or dust that's moving on top of the carbon dioxide frost. There are lots of new gullies forming in the dunes. A couple of examples here. Here's an example where This channel right here, which is 5 meters wide, so that's, you know, almost the size of this front counter here, wide and probably a meter deep. That's a new channel. That's a lot of sand that moved downhill in just this one season, basically. Here's another example and a couple of things. First, you can see this channel here and a little alcove. That's completely new. Wasn't there at all. These are images that are separated in time by only, you know, weeks. We had a whole series of observations here. And then here you can see there was some gully activity, but the channel has incised more deeply here and again here. Again, this is happening in the winter when there's CO2 frost on the ground. There are also these strange linear channels or linear gullies that have pits at the end of them. And we're not sure how these form, but these are active too. And here's a little 2-time step. And up in this region, you can particularly see a lot of new pits forming. And there are some new small channels as well. Again, we don't know for sure how this forms. One idea is that blocks of ice slide down the dune and then the ice sublimates and leaves these pits, but we don't really know yet. Here's a scene where we see these dark dust devil tracks. We see those commonly on Mars, but something different here. We see these little dark streaks coming out from the bedrock. And this is a very different type of activity because this happens not when there's CO2 frost in the ground, but in the warmest time of the year, in places that get quite warm. And these things fade away in the cold season and reform each year in the warm part of the season. So this is very intriguing, and we're still debating and analyzing data and acquiring new observations to try to understand this more fully. Potentially, this could be briny water, actually water flowing on the surface, but that's just one hypothesis. As the dry ice sublimates, it creates all sorts of fanciful patterns. Here's one sequence. This is a sand dune. We get spots and streaks that then darken and brighten, get bright fringes, more streak activity, very, very dynamic. Here are some slopes from dunes where these streaks form, and a clue to what's going on is that here we see a little dust cloud. It's kicking up a little dust as it moves, and probably this red material around it. We think this is sand that's flowing, but it kicks up some dust in the process. Here's a sequence showing before, during, and after. The activity is in the winter when there's CO2 frost, but then we see that new gullies have formed, sand has moved. Here's another sequence, before, top, during, in the middle, and after at the bottom. And there's also whole new ripple patterns that are formed here, very, very active. These are 8 images of the same patch of ground on Mars, believe it or not. And this is a sequence extending from late winter into early summer, just showing all of the things that happen as the CO2 frost sublimates. So in an earlier time step, it was completely white, covered with frost. And then we start getting these spots. The spots grow, they deposit dust. Then some of these start turning bright blue, perhaps from new frost deposition. This terrain down here behaves differently and has more reddish dust on the surface, but then that changes. This changes, some areas darken, some get brighter. Eventually, and this is now a different stretch to this image where it's really quite dark. Eventually the frost is all gone. Okay, and then there's on the South Pole, there's a residual cap of CO2, and that stays there all summer long, but it stays there, but it doesn't stay put. We call this the happy face, and this is a pit. Now the sun's coming from this direction. You see his smile, his nose, and multiple eyes or something. But here's a little time sequence here. And you can see how it's changing, where all of these pits are growing in size, so it's eroding at the margins. And you can see over here some little features on the edge there that get to almost disappear. The smile here wasn't quite connected before, merges, these pits. When this sort of activity was first seen on Mars, the first interpretation was the CO2, it's disappearing. It must be global warming on Mars. There were some people who went, aha, there are no people on Mars. That proves people don't cause global warming. That doesn't really follow. It does follow on Mars. People don't cause global warming on Mars. Okay, I agree. But also, there's probably no global warming on Mars. We now think that the CO2 that sublimates gets redeposited on nearby plateaus. And this is happening so fast that this cap would disappear in, less than a century, and would have been much bigger just, 50 years ago. We have observations, and this isn't happening. So now later in the summer, the happy face starts glowing, and that's this process of redeposition of frost along the edges here. And then in late summer, this is about as frost-free as it gets, where there's patches that don't have frost on it or ice on it. And to summarize then, Mars was very active in the past, more Earth-like, with volcanism and floods and channels and so forth. But it's still very active today. We estimate that bolides hit Mars more than 100 times per year and make sometimes fields of craters. Sand ripples are on the move over many regions at all latitudes. Steep slopes are active with streaks and boulders flowing downhill and gullies. There's lots of activity in the regions covered by this dry ice in the winter. And the South Pole residual cap is especially dynamic, forming, it's like reincarnation where it's constantly reforming its shape. And I'm going to stop there and take any questions. Thank you.
Start right here in the middle because I saw your hand go up first, and what I will do is repeat the question for folks online, and then Alfred will answer. If you've only looked at 1.2% of the surface, how do you decide what's next? What's the structure of the campaign?
Right, so we have an elaborate process where first people, including all of you, can go to our website and enter suggestions for where to image on Mars. It's called HiWish, or the HiWeb website. So lots of people, including the team, members of the science community, and the general public, enter these targets. And they're each assigned to a science theme. And then if you assign it to landscape evolution, John Grant here is the science theme lead, and he gives it a priority. And then we have a lead scientist for each 2-week cycle, which John is doing here for a cycle coming up. and they take all these prioritized observations, select on them, and make additional decisions about which ones are most interesting, which ones are time critical for the particular season we're in, and where the lighting is good. So we have sort of a 3-step process where we winnow this down, and we also have to deal with the fact that there are these other annoying instruments in the spacecraft that want to point the spacecraft in different directions. So we don't always get our wish, and then we have backup options. And through this whole process, we come up with our list for each cycle.
Okay, up behind you a few rows. Yes, sir. You commented that the surface sublimates and then is redeposited. Do you ever notice that it snows on Mars?
That's a great question. We can't see in the dark, and we see this CO2 form every winter and sublimate in the spring. And so there's basically 2 ways it could form. One is that it condenses directly from the atmosphere onto the surface like frost, but the other way is that it snows. Well, the Phoenix lander had a fun instrument contributed by the Canadians, a LiDAR that shined laser up into the sky to study the atmosphere, and they actually detected snow up there. So they've confirmed that it snows. I'm not sure that snow that they saw made it to the ground or not, but it does snow on Mars.
Let's come over here in the blue shirt.
Just judging by the pictures and the scale, some of these ancient lakes look like they were many meters deep. Is that accurate?
Judging by the scale of the images, it looks like some of these putative lakes were many meters deep. Is that an accurate interpretation?
That's correct. In fact, some of them could have been even hundreds of meters. So, yeah, very deep lakes. And then there's still debates about whether there were even lakes or small seas. Maybe the Hellas Basin could have been filled up, or the northern plains, where now we're talking about more than a kilometer, say, depth of water. That's still controversial. It's not as definitive, but lakes 100 meters deep are pretty widely believed at this point.
How about way in the back? You got to yell so I can hear you.
Yeah, have you seen any of the Mercury pictures, and how would you compare our interest in Mercury with our commitment to Mars?
Have you seen any of the new messenger pictures of Mercury, and how do you think they compare to the kinds of things that we're seeing on Mars?
Okay, great question. Mercury doesn't have an atmosphere to speak of that influences the surface, at least. And what we see there are impact craters, lots of them, better preserved. They're not eroded like on Mars. There's also lots of evidence for volcanism on Mercury. And there's a regolith, there's soil, there's mass movement, boulders tunneling down the hill. So a number of things we see on both Mercury and the Moon and Mars. But then Mars has some additional things, these wind-blown dunes. Don't see that at all on Mercury. We don't see the carbon dioxide seasonal frost and deposits, but Mercury does have these interesting deposits in these permanent shadows in the polar regions, which might be water ice, but one theory is also that it's sulfur, actually. So that's one of the questions that they'll try to address. So there's some differences and some similarities.
I haven't been over here yet, so. Is it true that one of the poles on Mars is mostly water ice and the other is CO2 ice?
You're half right. There is one pole that has the CO2 residual cap that lasts all through the summer. That's the South Pole. But both caps have lots of water ice. In fact, the South Polar cap probably has more water ice in it in the subsurface layers than the North even. So why this difference? Well, there's an asymmetry of the seasons where, I mean, we have winter and summer like on Earth. On Earth, winter and summer, summer in the Northern Hemisphere is about like summer in the Northern Hemisphere, except for all the differences in the land masses and circulation patterns. But what happens on Mars is that it has an eccentric orbit. So during the southern summer, it's short and hot. So we're closer to the sun. It's a shorter season, but hotter. And then the winter is longer and colder. So that there's an asymmetry, and that asymmetry changes every 10,000 years or so. And so, if we went back 10,000 years, it might be reversed, where the CO2 is in the North cap and not the South.
Yeah, here in the middle.
There was a hypothesis that the northern lowlands are one big impact basin. Has HiRISE shed any new light on that issue?
The northern lowlands have been hypothesized, among other things, to be the result of a very large impact. Has HiRISE shed any light on that?
Okay, you're right. That's a theory that seems to be gaining a lot of traction. It seems like a good theory. With HiRISE, we're zooming in on such a small scale relative to the scale of this feature. We see rocks. We basically see younger activity. As you go to smaller scales, you tend to see evidence for younger activity. So we can see the boulders, we can see the polygons, we can see what happened in recent thousands or millions of years, but it's not a good way to understand what happened 4 billion years ago, at least in terms of a physical process of that scale. You can learn something about the mineralogy and structures in the rock. Potentially we could see something that would support that, but we haven't in any event.
Here, and then I'll come over here.
What questions does HiRISE ask the sample analysis at Mars instrument on the MSL will answer?
What questions does HiRISE ask that the sample analysis instruments on MSL will answer?
Well, we get from HiRISE high-resolution images and color and stereo. We also, another very important instrument is the CRISM spectrometer, which looks at the surface in hundreds of wavelengths and can map out the mineralogy. So from those two instruments and other instruments, a whole suite of hypotheses form. And so, for example, in Holden Crater, we see these layers. We can see evidence of there being two major episodes of lakes. We can see something about how fine the layers are, but then the question is, was there organic material that was deposited and preserved in those layers? And that's a kind of question we can't answer from remote sensing. MSL has to go there and collect the samples and analyze it in the laboratory that the rover carries to answer that question.
There's a question here.
The fact that you've discovered clean ice on Mars was somewhat surprising. Is there any indication or evidence of how thick that ice is?
Finding clean ice on Mars seems somewhat surprising. Is there any evidence as to how thick that ice is?
There is evidence. In some cases, some of the bigger craters seem to have excavated through the clean ice. And it's kind of a crude measuring device looking at all these different craters in different places of different sizes. We also, from the Phoenix lander, they dug a trench, and they also found this very thin lens of clean ice that was only centimeters thick. We think it could be up to 1 meter thick, but in general, it's not terribly thick. It's basically a thin lens of clean ice that sits on top of what is probably the dirty ice.
Okay, I think we've got time for one or two more, so I'll go back over here.
Are there websites where we can see HiRISE images?
That's a planted question, must be. Are there any websites that you can go to see HiRISE images?
Yeah,
and the answer is?
Yeah, I was stupid not to put that website into my talk. What was I thinking? But it's just http hirise.lpl.arizona.edu, or just Google, type HiRISE in Google. It's the first thing you see. And that website will also take you to HiWish, where you can enter suggestions. And there's a separate page that comes up for every image where there's different image products and there's information about it and so forth. So just Google or whatever you use, HiRISE, and it'll take you right to it.
I think there was one back here. How about in the middle there, the woman with the glasses? She's heard rumors that the relationship between ESA, the European Space Agency, and NASA has soured. Has that influenced any of these ongoing missions?
Great question. I think there's been somewhat of a misunderstanding whereby there was the decadal survey of planetary science, and they were trying to fit things into strict cost, be realistic for once, and come up with a plan that actually fits the budget. And the next mission for 2018 was planned to be 2 different rovers, one from ESA and one from the United States, landing together. But the trouble is the landing system to land 2 of these was too expensive. And so they costed an option where there was just 1 rover. And that actually fit within the program, that option. And so the impression that our colleagues at ESA got was that they're throwing our rover overboard. That's really not the intent. It was more, that was an example and it was something easy to cost. And now there are these discussions going on between NASA and ESA to come up with, so what is the plan? And there was an article in BBC that just came out with some early reports about they're planning 1 rover, but it's from a combined rover from the Europeans and NASA. So some solution will be found. It's still a disruption from the former plans, and it's going to be a bit agonizing, but we'll get through it. And yeah, these are the hazards of this business with international collaboration. Is that you have to be diplomatic.
Okay, I would like to thank Alfred very much for a great lecture. I would also like to thank our sponsors, Aerojet and NASA. Again, thank you. And you're giving me the thumbs up. Does that mean it's okay? So for those of you that are interested, the public observatory is now open for telescope viewing. Also, I think most of you got a survey that you were handed when you came in. Please make sure that you fill that out and turn it in as you leave. One lucky winner will get, or one lucky person will receive a door prize. And then finally, be sure to come back on May 12th when Sean Solomon will be here to talk about the new results from the Messenger mission at Mercury.
Yeah. Also, there were HiRISE posters. I see some people have them. Are there any more of those?
I don't know. Are there more? Probably. Sounds like there may be more HiRISE posters out front.